years, we've seen electronics get smaller and thinner. Compare this bag phone to the modern iPhone.
Or this computer from the 90s compared to this Apple MacBook from 2019.
This has been made possible by nanoparticles that have been used to provide high-speed data transmission between circuits. They allow for smaller, thinner, and more flexible electronics.
The electronics being developed today are smaller than previous models, but store more information than ever before thanks to nanotechnology.
But the innovation doesn't stop there. Nanoparticles are being used in a number of medical and agricultural applications.
Nanotechnology is the branch of technology that manipulates individual microscopic molecules and atoms called nanoparticles.
Nanoparticles have one or more dimensions that are shorter than 100 nanometers in length. Essentially, they're smaller than a tenth of a human hair. Tiny, right?
In short, small particles make a big difference.
In today's collision course, we're going to be diving into nanoparticles, more specifically metallic nanoparticles.
Metallic nanoparticles are particles made of metals and their oxides, which are smaller than 1/1,000,000th of a meter.
There are many examples of nanoparticles in historic objects. Stained glass windows, the Lycurgus cup from the 4th century, and the first types of photos, daguerreotypes, all contain metal nanoparticles. Back then, they didn't understand the tiny technology that they were using.
Not until 1857 when nanoparticles were originally observed by Michael Faraday. He was the first to recognize the existence of metallic nanoparticles in solution. He observed the variation in the color of solutions based upon the size of its nanoparticles, especially with gold nanoparticles.
In 1908, Gustav May, a German physicist, gave the quantitative explanation of the color in solution. We are used to seeing gold and yellow. However, when gold is in the form of nanoparticles, it interacts differently with light depending on the size and distance between the gold nanoparticles. They can appear red, orange, or even blue in solution.
It is clear from the gold nanoparticles that they have different properties than the same materials on a larger scale.
How is that possible? They're the same thing.
These differences are due to variations in electron structure. The high number of atoms on the surface of the particle, increased unsaturated bonds, and variations in their band gap.
Metallic nanoparticles have a large surface area to volume ratio. This larger surface area means the particles have greater contact with its surroundings. Take balloons for example. A balloon without air in it will not touch much of its surroundings because of its low surface area.
Anyways, balloons with air in them have a much larger surface area and will therefore have more contact with their surroundings.
Their larger surface area makes metallic nanoparticles effective catalysts, meaning they can be used to speed up chemical reactions.
Thank you for the demonstration, James, but let's get back on track. Metallic nanoparticles also have high surface energies, meaning high attractive forces. This is important in bonding.
Metallic nanoparticles can be modified with different functional groups to bind with antibodies, ligands, and drugs because of their high surface energy.
Metallic nanoparticles also have a large number of coordinating sites. A low coordination site is a place where there are not many things bonded to the atom.
Low coordination sites can also be described as unsaturated, meaning that they have some double or triple bond.
These low coordination sites have the potential to store more electrons than it does currently. Examples of this are corners and edges of the nanoparticles.
These properties make metallic nanoparticles particularly useful in many fields of study.
Metallic nanoparticles are synthesized or chemically produced so that the particles will have a defined size, dimension, composition, and structure.
Whoa, hold on! We need to make sure that metallic nanoparticles are synthesized in a way that is reproducible, controls the shape of the particles, yields dispersed metallic nanoparticles of uniform size, is easy and cheap, uses less toxic precursors, uses reactants conservatively, uses a reaction temperature close to room temperature, and has as few synthetic steps as possible, minimizing generated byproducts and waste.
You may be thinking, if nanoparticles are so small, then how can we study them?
Don't worry, there are many techniques used today that help us learn more about metallic nanoparticles. For example, in UV visible absorption spectroscopy, a spectrophotometer is used to determine the optical properties of nanoparticles. Optical properties describe how the particle interacts with light.
Oh, and X-ray diffraction (XRD) analysis uses X-rotoflex diffraction meter to establish the metallic nature of the particles.
Here's another: Fourier transform infrared spectroscopy An FTIR spectrometer measures infrared intensity versus wavelength of light to determine the nature of associated functional groups and structural features of biological extracts with nanoparticles.
Microscopic techniques such as transmission electron microscopy and scanning electron microscopy have been used to prove that nanoparticles are relatively uniform in size and shape.
C. Scientists have developed many techniques over the years so they can study the ins and outs of metallic nanoparticles.
Why do we care about nanoparticles? What do they offer us?
Metallic nanoparticles enhance Rayleigh scattering, which is the scattering of light by particles in a medium without changing the wavelength.
They also enhance Raman scattering, which is the inelastic scattering of photons by matter. This means there is an exchange of energy and a change in light's direction.
They also offer strong plasma absorption. Plasma is a hot ionized gas consisting of approximately equal numbers of positively charged ions and negatively charged electrons.
They help with biological system imaging as well, which allows us to see particular structural or physiological characteristics.
Lastly, they help determine chemical information on metallic nanoscale substrates. A substrate is a molecule acted upon by an enzyme.
It sounded crazy, but in short, metallic nanoparticles help us learn a lot more about our world and have many applications, which we will get to later. The applications of nanoparticles will make why we use them make a lot more sense.
However, with these amazing advantages, there are a few disadvantages that must be considered when dealing with metallic nanoparticles.
One disadvantage is particle instability. Because of this, retaining the structure of the nanoparticle becomes difficult.
Another is impurities. If the environment the metallic nanoparticle is being synthesized isn't pure, the nanoparticle may contain impurities and be harder to work with.
They can also be biologically harmful. Nanomaterials have been reported as toxic, carcinogenic, and can cause irritation to the skin.
One risk of metallic nanoparticles is the risk of explosion. Exothermic combustion can lead to explosion, as fine metal particles often act as strong explosives.
The last disadvantage is difficulty in synthesis, as the nanoparticle must be completely contained to maintain the proper size.
These disadvantages should not discourage us from using metallic nanoparticles. Scientists working with them have developed ways to avoid these as much as possible.
What company do you work for, and what is your job at the company?
I work for a Japanese company called Shoei Electronic Materials, and my responsibility is I'm Vice President of Sales and Marketing for the Americas and Europe.
What kind of education did you have to get to that point?
I have a bachelor's and PhD in chemical engineering.
What would you say makes nanoparticles so special?
The unique thing about nanoparticles, I think, is that so many of the atoms in the particle are near the surface. When you look at bulk materials, only a small percentage of the atoms in the material are near the surface, and most are bulk. And what happens is the atoms near the surface, whether it's a bulk material or a nanomaterial, behave much differently, physically, chemically, electronically, optically. And so when you make particles of matter really small, where most of the atoms are near the surface, they have some strange behaviors that we can tailor for our purposes.
How were you first introduced to the world of nanotechnology?
I spent most of my career in research and development in the electronics industry, either producing materials that are used in producing electronic components or actually manufacturing electronic components. And as you know, the electronics around us keeps getting smaller and smaller. And in order to make the electronic devices, smaller, we end up having to use smaller and smaller materials. For instance, much of my career has been involved in the manufacture of multi-layer ceramic capacitors. They're tiny devices that you find on circuit boards, and the world today is using over 4 trillion multi-layer ceramic capacitors a year. You can buy 10 of them for a penny on average. And these things, when I started my career 35 years ago, they were composed of maybe 20 or 30 layers, and each of the layers were 5 to 10 microns thick. In today's most advanced multi-layer ceramic capacitors, and 1,000 layers of conductive material combined in a tiny chip, and the individual layers are 1 micron or less in size. To make such very thin layers, we have to use smaller and smaller particles. The particles we use in this application have gone from micron-sized particles to nanoscale particles.
Throughout your career, how have you been able to apply your knowledge of nanotechnology nanotechnology to your everyday life?
That's a really hard question to answer. So the work that I've done with my colleagues in being able to reduce the size of electronic components, I guess I was in my 30s when cell phones were first developed. They called them bag phones. They basically carried around a bag. Now carry around these tiny devices that have computers that are more powerful than the mainframe computers, the size of a large room. And that's all because of this downsizing materials that allow downsizing of electronic components. The miniaturization of electronics has really had a big impact on our lives.
How may curious students pursue a career in nanotechnology?
People that are discovering, they're basically out to discover new nanoparticles and behaviors of nanoparticles. They would come through the fields of physics, perhaps, or chemistry, or material science. They find particles that have useful properties. Somebody has to figure out how to scale that up. So there are chemical engineering degree that was really useful. Then you get other people in terms of, all right, using these things. Again, somebody's got to figure out how to use them in devices. And you have electrical engineers and you have material scientists. So there's various ways you can get involved.
What kind of positions exist in the nanotech workforce or at your company?
We have people that are doing research and development in a couple areas. My company is really good at taking a laboratory process and scaling it up. We have people that are looking at ways to manufacture semiconductor nanoparticles. Most of our work is focused on producing metals. We're constantly trying to figure out how can we make them more productively at lower cost? How can we better control their properties? So a polycrystalline particle will behave quite a bit differently than a single crystal material. So we've got people looking at that. And then we have people in manufacturing that are basically keeping the equipment running and trying to decide how can we make the equipment operate at higher efficiency, improve the yields, reduce the cost. And then you have people like me that are out talking to customers, looking for new applications for our particles, I attend conferences and workshops, trying to find new market opportunities for the company.
Thank you. You gave us a great inside look at the world of nanotechnology, so thank you very much.
After speaking with Larry Mann, we want to take this time to talk about more jobs that are associated with metallic nanoparticles.
Typically, when we think of nanoparticles, we think of the engineers and scientists doing research on them or developing things from them.
Okay. An example of this is a nanosystems engineer. Nanosystem engineers design, develop, or supervise the production of materials, devices, or systems of unique molecular composition.
Then you need the people who aren't doing the research like me, but manage these projects. This is the job of the technical program manager. They are responsible for initiating programs, following their progress, and fixing issues that arise.
You also need people to market the products that nanosystems engineers are developing. This is the job of the product marketing manager. The product manager's job is necessary because metallic nanoparticles have many applications.
We've been talking a lot about what metallic nanoparticles are and how they're unique, but now it's important to talk about how we use them.
One of the largest sources of funding for nanotech is the Defense Advanced Research Projects Agency. The military does a lot of work with nanoparticles.
The Air Force uses aluminum nanoparticles to create ammunition that takes up less space on the aircraft but is just as effective.
The Army has created a class of amplifying fluorescent polymers that detect hazardous substances with extremely high sensitivity using nanoparticles.
The Navy developed a cobalt-rich nanocrystalline alloy that was tougher than the iron magnetic alloys being used to create motors.
Imaging sensor, display, solar cell, photocatalysis, biomedicine, optical detector, laser. These applications are all based on the optical properties of metallic nanoparticles.
They have also been used to speed up chemical reactions, a process called catalysis. These MNP catalysts are highly effective and last a long time.
They are also used in sensors. Sensors help monitor reactions and give data in real time. They are very useful in many types of research.
Metallic nanoparticles also have medical applications. In cancer treatment, gold nanorods can be heated using infrared light in order to heat and kill cancer cells.
Currently, researchers are producing antimicrobial nanoparticles using plants. These are generally safer for the environment and used in other organisms.
Overall, metallic nanoparticles have so many applications. The way that we use nanoparticles increases every single day.
Products that contain nanoparticles or use nanotechnology are regulated just like any other product by the Food and Drug Administration. They consider the unique properties of nanoparticles while assessing them.
The effects of nanomaterials in the particular context of each product and its intended use are considered during the technical assessment.
Depending on the type of product, regulations may be more strict. Nanoparticles used in drug delivery, for example, would be evaluated based on their risk and predicted benefit.
The company must inform the FDA about the safety effectiveness, and regulatory status of the product.
The FDA encourages manufacturers involved with nanotechnology to consult with them before putting their product on the market.
The products using nanoparticles and nanotechnology must be continually monitored once marketed.
There are a few ethical issues surrounding nanoparticles.
Because we use nanotechnology in so many ways, some people believe that nanotechnology will give us godlike powers. They believe we can control too much.
Whoa. Another thing people think is that nanotechnology can lead to undetectable surveillance.
Get out, Murray!
Anyway, there is some debate about what international laws can be made about nanotech and how different fields can synchronize their policies.
Yeah. What we really need to talk about is the gray goo scenario.
It's not this.
Yes, this is a huge problem. It could really happen.
Okay, explain. What is the gray goo scenario exactly?
The gray goo scenario is the idea that self-replicating nanomachines will get out of control and consume all the biomass on the Earth in the process, reducing the entire Earth to gray goo.
Dun dun dun.
Okay, everyone, that's the end of today's collision course.
We hope you learned a lot about metallic nanoparticles and why they're important in so many fields.
And gray goo, beware!